Greetings, ladies and gentlemen. This is a tutorial for lab number 3. It has two sections, lab 3.1 and lab 3.2. In lab 3.1, we are going to examine the equivalent, Thevenin equivalent circuit for a given design, which could be a complex design in a general sense. And in 3.2, we are going to go through the maximum power transfer and verify the concept of the maximum power transfer. I'm going to go through the Thevenin. We have had the lectures on Thevenin and Norton source transformation. Some of them are actually posted now. If you want to go into details and see a better perspective of it, please do so. Now, here is the main idea. I have a design, and in this design, I have a bunch of independent voltage source and independent current source and a number of fixed resistors, something like that. Now, I do have a load, and from load perspective, whatever is happening inside is not really of a concern. I want to see if I could replace this block with this simple design. We did achieve that when we did talk about the source transformation. Through a consecutive change of topology, we were able to change the voltage source in series with the resistor to a current source in parallel with the resistor, and then change parallel components to one component and eventually get to this shape. This is a very simple shape. We consider that as a building block. So we would like to see if we can actually simplify all that is happening inside, however, to make sure we capture properly and correctly whatever is happening at the outside. So I want this to be the same as this. Now, there are things that I need to watch for. I need this voltage, for example, which I'm going to call VL, to be the same as this voltage, because that's what matters to me the most. What matters to me the most is the load itself. IL versus IL. I want to simplify this design, and when I replace this, I want to get the same VL, the same IL at the end of the day. Now, given the values for R1, R2, R3, one simple technique of achieving this would be to do a source transformation. So let's go back, and I want to see how I can achieve that. I have a game plan. The game plan is this. If I identify a voltage source and a resistor in series, I know that I can change that to a current source and a resistor in parallel. If I have a current source and a resistor in parallel, I know I can change that to a voltage source and a resistor in series. But there must be a reason for each step I take. Now, if you take a look at this one, I have a series resistance and a voltage source. When I change that to a current source and a resistor, the reason this might be beneficial to me is because this resistor, when I replace this part of the block with this segment, is going to be in parallel with R2. So I need you momentarily to look at this in an isolated scenario, just this segment, and tell me how much is my current and how much is my resistor going to be. As we discussed, as a source transformation technique, the resistor is going to be exactly the same. So no harm, nothing difficult. It's a cut and paste of the value. It's going to be a current source for sure. And I need to identify the direction. Now, if I take this in my mind, and that's going to be R1, and this one is going to be basically Vs. As an isolated element, if in my mind, just momentarily have this shorted, I need to have this one shorted as well. I want to have the same behavior outside. Now, if you take a look at this is plus, this is minus, and you have R1 in the loop, obviously the current is going to go like this. Therefore, the current in the short line is going to be like this. I need to make sure I assign a current direction so that when I have a short, I would have the same direction on that short line. Now, considering the fact that the people come in, they see resistance and they see no resistance to achieve and to go to the same destination, which would be at this node, I can imagine that this direction will satisfy my criteria. the current come in, everybody goes through the short line. That's going to be satisfying because they are matching with the short in the original design. How much is this current? Obviously you have Vs applying itself across Vr, and therefore this current is going to be Vs divided by R1. Vs divided by R1, that's the current, and that's what I'm going to say. That's the current. Now I know how to replace this segment. I'm going to remove this segment, and now I have the luxury of replacing it with the new model. Let's simplify this. This is what is going to replace at this moment. That's going to be R1. The same R1 is going to remain there, and this one is going to be a current source. This current source is going to be Vs divided by R1. Now I am in a better position because R1 and R2 are in parallel. I can combine them and have one resistor in front of me. So let's take a look at this. These two resistors, R1 and R2, would be in parallel, and only for two resistors in parallel, I can use a simple formula. And this simple formula follows the G rule we talked about. It's going to be R1, R2 divided by R1 plus R2. That's going to be the resistivity of this. You can also follow the G rule, and the G rule would say 1 over R equivalent is equal to 1 over R1 plus 1 over R2. You take the common denominator and you find and you come to the same conclusion. This is only true for two resistors. It's not valid for three resistors in parallel. So keep that in mind. Now, what do I have and what do I want to achieve? I want to have this structure. I can't see this in series. I can't see them in parallel. And that's a block, a roadblock for my simplification process. But I do see something in front of me that's going to help me to actually reform and have it better. If I have this in mind, a current source in parallel with a resistor, and if I do one more source transformation, that source transformation is going to help me to basically change that to a voltage source and a resistor. So let's grab this. I want to replace this with a voltage source. I don't know what the polarity is. I know what the resistor is going to be. The resistor obviously is going to be R1, R2 divided by R1 plus R2. That's what the resistor is, right? Now the question is, what is the polarity of my voltage source? Now, if you isolate this block and you see that the current is coming in and hitting the voltage, the resistor on top, I can feel that there is going to be a plus and a minus if this is isolated. A plus on top and a minus at the bottom, that's going to be simple enough for me to make a conclusion. Plus on top, minus at the bottom, minus at the bottom. How much is that value? All I have to do is to multiply this. The current comes in, hits the resistor, Ohm law. So basically this one is going to be Vs R1 times R1 R2 divided by R1 plus R2. I can simplify this. R1 and R1 is gone. You can see that I can replace this segment of the design with new transformation. I'm going to have one resistor. That resistor is going to be R1 R2 divided by R1 plus R2, and then I'm going to have a voltage source. You can see from the shape I'm extremely close to my destination. R2 divided by R1 plus R2. All I have to do is these two. That was my plan right from the beginning. You need to see how the structure is coming into play to get you to your destination, which would be one resistor. So let's take a look at this. These two would be in series. I can easily conclude that R Thevenin is equal to R1 R2 divided by R1 plus R2, then plus R3. That's your Thevenin. R Thevenin. And V Thevenin is going to be the same as this. Nothing is going to change in that sense, so it's going to be Vs times R2 divided by R1 plus R2. The entire idea in this lab is this. We would like to build the original design without any manipulation or change of the topology. We would like to build the original design and understand the behavior of the design at the output. RL is going to be changing. I'm going to show it to you in a moment. RL is going to be a changeable variable resistance. So RL is changing from some small value to some high value to simulate a kind of a short at the beginning and a kind of an open at the end. Obviously, we attempt not to short because it may not be safe depending on the structure you have. So we are going to have the original design, we are going to have RL in front, then we are going to replace this with the new one, and we are going to see, do we get the same behavior? Do we get the same linear behavior we expected to see from the point of load, from load point of view? And that's what the intention of Lab 3.1 is.